for method of sections. So it's a method of sections double. You'll be asked to identify a couple of zeros. Oh, and by the way,
It's for the quiz.
there was a shitload of zeros on that trust product. Like both middle sections were all zeros. E and G. If you're going to look at left half, you need B. If you're going to look at right half, you're going to look at and find E and G. Well, we've already done all this info because go back when we did this frame problem, you'll see that we found Bx to be 666.67. By we found to be 2,000. Ey, which is here, we found this to be, well, Ex, we found this to be 1333.33. We found Ey to be upwards and a value of 4,000. And we also found up here at G, we found this to be Gx of 2,000, Gy of 2,000. So this all came from the frame analysis. So if you were doing a frame problem and you wanted the internal forces, then you would have to do a frame analysis in order to find these values. Now this section 2.2 sits right here. That's 2.2. And like I said, you could look at either left half or you could look at right half. Up to you, it doesn't matter which half. I'm going to pick left half because there's a whole lot less shit on the left half than there is on the right half. So I'm going to come in and I'm going to say, free body diagram, cut 2-2 LH, left half. Well, that's going to give me this. 666.66, 2,000. And then I'm going to have an axial, a shear, and a moment. Let's call this point Q. So when I draw this up, this is what I should have. I should have an axial to balance out x's. I should have a shear to balance out y's. And I should have a moment to balance out any rotational effects. Now, there is another one that we talked about, and that is the torque that twists this along its axis. We're not talking about that one. We'll leave that one for the next class. Now, how I pick these directions, totally arbitrary. Just like picking the AX, AY, totally arbitrary. If I pick correctly, I get the right, positive answer. So here you can see that A minus plus 666.66 equals 0. A is equal to 666.66, but it's got to be headed the other way. I'll get a negative. If I do a sum forces in the y equals 0 positive up, I should get a V minus 2,000 equals 0, or V equals 2,000. If I do an M, some moments at Q, and I'm going to take counterclockwise positive equals 0, this will be M plus 2,000 times 1 equals 0. M is equal to minus 2,000, or what you're saying is M equals 2,000, but it's not clockwise, it's actually, it's not counterclockwise, it's actually clockwise. So that takes care of finding the internal force on a frame at position 2, or cut 2. I'm going to do the same thing for cut 1. Except with cut 1, I want to look at the upper portion of the cut rather than the lower. So I look over here, and I'm going to look this way. Well, by looking this way, I'm going to avoid everything underneath. So I'm going to say, free body diagram, cut 1-1, upper half. This is, if you go back to frame analysis, you'll see that this is CY 200 CX 666.67. Then I'll have the actual member, and here's the cut. I'm going to call this cut point P. Now on this cut, I'm going to have an axial along the axis of the member. I'm going to have a shear perpendicular to that member, and I'm going to have a bending moment, M. Again, all these directions in red are arbitrary. True or false? The axial force is always along the x-axis. False. Right here, when it's vertical, A happens to be along the y-axis. When it's horizontal, it's going to be along the x. So depending on the orientation of the member, the axial could be x or it could be y. And again, I'm going to do a sum forces in the x equals 0, positive downward. Positive to the left. That's going to say 666.67 minus V equals 0. V is equal to 666.67. Sum forces in the y equals 0. Positive upward. 200 minus A equals 0. A equals 200. And some moments about P equals 0. Clockwise positive, that says M minus 666.67 times 2 equals 0. I'm getting the 2 because it said section 1-1 is 2 feet from pin C, and section 2-2 is 1 foot from pin B. So this says M equals 1333.34, and it is clockwise. So that takes care of a frame problem. Now, what's the ultimate goal? The ultimate goal is to draw the shear bending moment diagram. It is not to find it at a particular point. Why do I want to draw the shear bend? Because I can visually see what's the largest value, because that's what's going into the equations in mechanics of solids or mechanics of materials. And that may not be at position or cut 2-2 or 1-1, it may be someplace else. I need to be able to draw that up. Now, to that end, you will see on page 143 how we accomplish drawing and finding the equations of the shear bending. So this problem's already pre-worked out. I'm going to walk you through it. I got A and B pinned and roller, and then I got some arbitrary load P. And I'm not putting a load, I'm just generically going to solve this problem with an arbitrary load. So wherever P is, you can put 100, 200, 300, 1,000, whatever. Well, when I draw the free body diagram to find the support reactions, this P sits smack dab in the middle. So half the load's going to the left and half of it's going to the right. As you can see, that's exactly what ends up happening. AY is P over 2, BY is P over 2, half the load goes to the left, half the load goes to the right because it's the load sitting smack dab in the middle. Now, Notice, I'm going to come over here and I'm going to make a cut before the load, and then I'm going to make a cut after the load. So I'm going to make two cuts. Here's cut 1-1 before the load. Here's cut 2-2 after the load. Well, if I draw the free body diagram of cut 1-1, I'm going to have this. P over 2, this is my AY, because I'm looking at the left half. There is no load here. There's a V and an M, and I don't care about A because I'm not drawing the axial diagram. So I'm going to leave that out for now. So there's my V and M, and they're in arbitrary directions, and I've made a cut at an arbitrary distance X. So I sum forces in the Y, that gives me V equals P over 2. I sum moments, counterclockwise positive, I'll get M minus this load, P over 2, which is AY. Since I'm summing at O, it's force times distance, so it's P over 2 times X. So M is equal to P over 2X. Well, that is really nothing more than Y equals MX plus B, with B equals 0 and M equals P over 2. So it's a line with the slope being P over 2 and the y-intercept being 0. So notice my shear is a value. So I start over here, which is AY. AY happens to be P over 2, so I'm going to go up P over 2. And it's going to stay the same, because you can see it stays the same. P over 2 is the same value as when it started. So that is a horizontal line across until I get to a load. P minus P over 2 negative plus this is equal to minus P over 2. So I'm going to drop to a negative P over 2. There's the calculation to get the P over 2 negative. There is no load, so it's going to stay the same until I get to the very end. By is P over 2, so I got a plus P over 2, a minus P over 2. Where do I go? 0. Every shear bending moment diagram must go to 0. That is got to happen. If it doesn't, then you screwed up someplace. You don't need ChatGPT, you don't need Chegg, you don't need me to tell you you fucked up. If it doesn't physically go to 0, you screwed it up. Now, do not try to fake my ass out. I've been doing this too long, and I can see a fake when I literally look at it. I would prefer you fuck it up and say, hey, I fucked it up. I don't go to 0, and I know it should go to 0. I'll give you more points for being honest with me rather than trying to fake my ass out. What's the moment diagram? Well, this is y equals mx plus b. Well, that's a line. So I got a line that's increasing up until I experience a load. So I can draw this. There's no external moment, so it starts at 0 and goes to this point. Well, what is that point? Well, if I plug P over 2 times L over 2, I'm going to get PL over 4. And that's exactly what you see there, PL over 4. Next, I'm going to make the cut 2-2. If I make the cut 2 and look at left half, I can look at right half, it doesn't matter. I happen to choose left half. There it is right there. There's the P over 2 for AY. There's the load. I've cut it now to the right of that load. At some arbitrary distance X, there's my V, there's my M. Some forces in the Y gives me P over 2 for V. If I do the moment at Q, I'm going to get M, which is this guy. Then I'm going to get minus P over 2 times X, that's this guy, times this distance X to get to Q, plus P times X minus L over 2 equals 0. So I'm going to get an equation for the M that looks like this. Again, this is my y-intercept, that's my slope. And so when I draw this, I'm going to draw a negative slope, and it's got to go to 0. The PL over 2, if I extend this out, that will cross over at PL over 2 at the y-intercept. Now, that's how you generate the equations for shear and bending moment, as well as the diagrams. Because once you generate the equations, then you can draw them. Oh boy, that's a pain in the ass. But how many are going on to MOS, EML 3500? Guess what? I know for a fact that the person that teaches it in the fall is going to have you do exactly this. Make the cuts, do some force X, some force Y, some moments, and find the equations literally, and then plot the equations. That is not how I would do it. But I know he does it that way. So you better get used to doing it that way. Okay? So to that end, trying this one out. This is page 144. Notice, here it is now. We got some numbers. First thing I did was I found AY, BY. By the way, what type of beam is this? What's this called? Overhanging. Correct. So notice I get BY, AY, perfect. Now I'm going to make a cut somewhere before BY, then I'm going to make a cut somewhere after BY. Here's the cut at C, say, before BY. Notice the only thing you see is AY, some distance X before BY. Then you got the A, B, and C, and I really don't give a shit about the A, but I threw it in there just for shits and giggles. Because all I want to do is draw the shear and the bending. Notice B is 20. M is equal to minus 20 times X. Well, that's the equation of the line with the y-intercept being 0. There's your slope. Draw that in. Okay? Then you make a cut after BY. There's BY. I made the cut after. There's the distance X. There's my shear B, and blah, blah, blah. B is still 20. M is now 200x minus 400. That is literally the equation of the bending moment. So now, when I come to draw it, I start over here at 200 because it's negative. It's downward. I start at a negative 20. It stays the same until I get to BY. BY happens to be 40. 40 minus 20 gives me a positive 20, so I'm going to jump up to a positive 20. There's no load until I get to the very end. I see a 20 down. Positive 20 minus 20 takes me to 0. I know I did this correctly. Over here, that's the equation with the y-intercept being 0. I'm going to draw a line that's sloping negatively downward until I get to here. Well, that's 10. 20 times 10, that's negative 200. So that value is negative 200. Then I'm going to have a positive 20x minus 400. That's going to be a positive value headed upward. So it's an upward sloping line that's got to end at 0. Does it end at 0? Check. For x equals 10 plus 10, 20. 20 times 20 is 400 minus 400. It is indeed 0. So these are the equations for these values. Yes? You win. I'm going to post this for you mechanicals because I know he's going to want to do this in his class for MOS. Okay? I don't want you to get screwed over and not know how to do this. Alright? Let's do this one. This one says, hey, tell me the internal forces at mid-span. That means sitting right here. Let's call this point C. Well, if I draw the free body diagram, I'm going to get A, Y, B, Y, AX, and a single force resultant, which is 50 times 10, which is 500, acting 5 feet here, 5 feet there. Agreed? This is external. That's what I should get. Tell me AY, BY. Well, we know what AX is. 0. I know that for a fact because it's a beam. Beams don't carry axial loads. That's not the intent of a beam. So what is AY, BY? Instant, without writing equations. Come on.
250.
Huh?
250.
Yeah. It sits smack dab in the middle. Half is going to the left, half is going to the right. So I know these guys are 250 and 250. Now, I'm going to make a cut through here. Remember, I had in the notes something very bold. Everybody remember what that bold was?
Make the cut first and then resolve the distribution.
Yes. You don't reduce, then make the cut. You make the cut, then reduce. So be very, very careful with distributed loads. You make the cut, and you reduce this down to this. A distributed load acting over 5 feet. That's 50 pounds per foot. Here's my AY, which I know is 250. And now that I made the cut, I have to put in my axial C, shear C, and I gotta put in my bending moment, MC. So now, what do I have? External, external, external. The internals have not become external, they've been exposed. So now I can say, hey, now that I have everything external, I really have a single force here, which is 250, right? 250 that way. This is acting at 2.5 feet here, 2.5 feet there. I now have an AC, BC, and an MC. Now, do your sum forces in the X equals 0, positive to the right. AC is 0. Sum forces in the Y equals 0, positive upward. That says 250 minus 250 plus VC must equal 0, or VC equals 0. Ah, very important. At the midspan, it's 0. Some moments, and let's call this Q, some moments at Q is equal to 0, and I'm going to take clockwise positive. That says 250 times 5 minus 250 times 2.5. This would be AY here. That's the load, single force resultant. Plus an MC equals 0. MC is equal to minus 625. Minus tells me, hey, goofy, it ain't clockwise. Or MC is equal to 625 counterclockwise. Now again, what's the ultimate goal? Draw the shear and bending moment diagrams. This is all at one particular point. It's not the shear and bending moment diagram. Correct? I can do it. And here it is. The long ass way. And here I just said, let's write it generically. So I'm going to write the W of X as 50. And I'm going to call this L over 2, L over 2. So you can see AY, BY is W, L over 2, W, L over 2. I'm going to make a cut here at C. And I'm going to sum forces in the X, sum forces in the Y. Sum forces, some moments. And there you have my equations for the shear bending moment. This is a line with a slope of W. y-intercept WL/2. This is my bending moment, which look, it's a parabola. It's x squared. So this is my A, that's my B, and my C happens to be 0 for the parabola. If you look, I'm putting in the specific data, which is W is 50, L is 10, etc. There's my shear, that's the equation of a line, and there's my parabola. And if I draw these up, notice, there's my shear, there's my parabola. So that would be the shear and bending moment diagrams for that. Now, this process of making a cut, reducing, and summing forces, that is a long-ass way of doing it. But I know for a fact the guy that teaches it in the hall is going to do this with you. So you need to be aware of this so you can see what he's doing. That is not the way I would do these problems. Okay? Let me show you what I would do. But in order for me to show you, I have to bring in a couple of facts. Let's bring in the facts. The facts are derivable. I ain't taking the time to derive it because I know you don't give a shit. So there's no reason for me to do it. Agreed? So, here come the facts. Oh, by the way, to draw shear and bending moment diagrams, understand that the graphs are abscissa. That's the fancy way of saying x-axis. Back in the 50s and 60s, nobody said x-axis. They said abscissa. So abscissa, or the x-axis, indicates the position along the beam. The ordinate, that was the fancy way of saying the y-axis, represents the value of the shear or the bending moment. So maybe if you want to use fancy words, abscissa and ordinate would be the words to use for x and y. Okay? These are the sign conventions we're using. If you're looking at shear, it is downward on the left half, upward on the right half. If you're looking at moment, it's counterclockwise on the left half, clockwise on the right half. These are completely arbitrary. You can switch them around if you want. But here come the facts. Again, derivable, I'm not taking the time to derive it. Fact number 1 says dv dx equals minus wx. Derivable fact. Again, all equations talk to you. You just have to be able to interpret what they're saying. What the hell is this equation really saying? What's it really talking? What's it saying to you? It says dv dx, slope. That comes from calc. Slope of my shear is equal to the force intensity of the load. So in words, interpret that as slope of the shear curve at any point is equal to the intensity of load at that point. That's what that, in words, that's what that equation is saying. And I want to challenge you, every time you go to a class and they write an equation, interpret it. Don't just say, ah, fuck, I got to memorize another equation. Because yes, you'll end up memorizing lots of equations, and you won't know what the equation's really saying to you. Equations speak, you just got to interpret their language. Okay? Now, in this format, I don't like it. It's not useful to me when it comes to solving for the graphs. Here's what's useful. You take that dv dx equal to minus w of x, and you do a separation of variables. How many have heard that phrase, separation of variables? 1 or 2 people. The rest of you weren't paying attention in calc. Separation of variables says put like variables together. There's an x, I'm going to say dv equals minus w of x dx. Now I'm going to integrate this. And I'm going to integrate this from v1 to v2, from x1 to x2. When I integrate this, this is going to say change in v is equal to v2 minus v1 is equal to the integral x1 to x2 of minus w of x dx. Somebody please tell me what the hell that equation says to you. Again, it's talking. Do you understand what it says? What's that equation say? Interpret that for me. What did that mean back in Calc 1? Yeah, that is the frickin' area under the curve. Under what curve? The force intensity curve. So this is the area under the force intensity curve. So here's the important fact you will need when it comes to drawing these real quickly. Change in shear equals the area under the load curve. I like that. That's useful. Stick with me here. Fact number 2 is going to come in and say the following. dm dx equals v. Again, interpret. Slope of my bending moment is equal to the shear. Again, in that form, not so useful, but if I separate variables, put the dx over with the v, etc., I'm going to get change in my bending moment from 1 to 2 is equal to integral v dx. Integral v dx is the area under the shear diagram. Voila! So the last 2 boxes, the last one I had here and this one, are the key elements that you need in order to draw these quick. Along with the table I'm going to give you. Here's the table. This is all in the videos. I'm not saying anything that's not in the videos. So if you're not getting it, watch the videos. Here's the aid you're going to need in order to solve these really, really quickly. Listen, if you have a constant load, a P, downward, 100 pounds, then my shear is going to be a horizontal line across and my bending moment is going to be linear, as you've seen so far. If I have a uniform distributed load, like a rectangle, my shear is going to be a line, and because it's dm dx equals v and you integrate, integration of a line becomes a parabola. If I have a triangular load, that means I have a linear force intensity. Integrate that, becomes a parabola. Integrate a parabola, becomes a cubic. They're all integrals of each other. Sweet cheese, wakey wakey. How can you sleep with me screaming? That must be a soothing voice. Really, really quickly. So let's go back to here. Watch. Shear. I know I'm going to start at 250. Because that's AY. AY was 250. BY was 250. Yes? Now what do I see right away? I see a distributed load. Correct? Uniform distributed load, that means my shear should be aligned. That's what that means. That line is going to cover from A to B. What's the area underneath this curve? 50 times 10. It's a rectangle. What's base? Base is 10. Height is 50. That is 500. Correct? So I have minus 500 plus the 250, which is AY. Change in my shear has to be a minus 250. Somebody got a ruler and an extra pencil? You have an extra pencil. Come on, Carpenter. I know you do. Give me that ruler. Thank you. So, what you're telling me is, I know from my chart, I have a line. That line's got to be this right here. And it's got to be, and it's got to end at 250. So my line got to be this. And I know it crosses at 5 feet, 5 feet. I know that for a fact. I didn't draw it exactly there, but that's got to be it. Now, why does it end at minus 250? Because I see a BY, which is positive 250, 250 positive, minus 250, where do I go? I'm going to shoot back up to 0. So I shot up from 0 to 250, down. Let's draw the bending moment. I know at 0 here, that's got to be a peak value. There is no moment out here. There's no external moment, so it's got to start at 0. What's the area underneath there? This is 1/2 times base 5, height 250. Yes? Or no? That's going to give me 625. So I know from here, hey, if I have a line, it's got to be a parabola. Okay, so I have a parabola. That's got to end at 625. Then I have another area here. That's going to be 1/2 times 5 times a negative 250, which is equal to negative 625. Negative 625 plus 625, it's going to go to 0, and it's going to go to 0 parabolically because this is still a line. So I'm going to go parabolically to 0. And that's how you do it quickly. Yeah? Yeah? What are these external loads? Downward or upward? That's a minus. Once I have a minus, I know a parabola goes downward. Remember, a parabola is ax squared plus bx plus c, right? If there's a negative here, that means it's downward. If it's a positive, it is upward. Right? Algebra. Now, I do want you to pay attention to page 147 and 148. There's some key features there. You need to read this carefully. Example. On page 148. When a concentrated moment is clockwise on your beam, the moment diagram rises. And if it's counterclockwise, it falls. Notice G. Maximum bending moment occurs at a point where the shear force crosses 0. Shear force crosses 0. So I need you to look at the guidelines for drawing shear bending moment, page 147 and 148. I'm not going to read the whole thing to you. You're capable of reading. But there's some hidden gems in there that you need to be aware of. Okay? That's just the way it is. All right. Let's take a look at this problem we're going to do together. I need to find A and B. Now, I'm going to give it to you because that's what's going to happen on the test. And by the way, these words are not going to change from what's in the test. Question number 2, test number 3 will be this problem. Draw me shear bending moment diagram. I have to test it. That ain't going to change your testing booklet. These are not going to change. So for example, here you go. For the beam shown, draw the shear bending moment diagram. Label breakpoints indicate where the shear bending moment might go to 0 if at all. For the beam shown, draw the shear bending moment. Label all breakpoints and blah, blah. It's the same words over and fucking over and over and over. The only thing that's going to change is that diagram is going to be different. That's the only thing that's going to change. These words ain't changing. They're going to be the same. The diagram is what's going to be different. Just so you're aware. And notice, on every problem that I give you, like for this one right here, those are your support reactions. You don't even have to calculate them. Oh, by the way, I have several people on the trust problem calculate the support reactions. Like, what the fuck are you wasting your time for? I gave you the support reactions. And one of them calculated wrong. I'm like, did you not look? I gave you the support reactions, 10 and 10 upwards. Anyway, I'm going to give you the support reactions here. AY is 4 kilonewtons upward. BY is 28 kilonewtons upward. You can find those. All you have to do is a chapter 5 equilibrium of a rigid body. Reduce that load of 5 kilonewtons per meter to a single concentrated load at known location, some force X, some force Y, some moments. You should be able to come up with AY, BY. Now, on the test, I'm going to give you those. Did everybody hear that? Yeah. Don't waste your damn time trying to solve for them. I'm going to give you those. I'm going to start you off wrong, then you can fuck it up from there. I used to not give them. And people will get those AY, BY wrong. Well, if you get those wrong, the whole shear bending moment diagram is going to be wrong. It'll never go to 0. So now I give them to you because I want to test you on the shear bending moment, not your ability to find AY, BY. Okay? All right. So now I start. Shear. It starts at A. A is 4, so it's a positive. It's upward, so I'm going to go here to 4. Then instantly, as soon as I move away from A, what do I see right away? Uniform distributed load. Uniform distributed load says, oh, I got to have a line. I got to have a line. Now, that line could be a line that goes from 4 to a positive number, could be a line that goes to 0, could be a line that goes to a negative value. So those are my Those are my possibilities. It could be a line that goes to a positive value, could go to 0, or could be a negative. Either one of those 3 is possible. How do I know which one? Find the damn area underneath the distributed load. So I come in and I find this area, that is base times height. Base is 4, height is 5. That's equal to a minus 20. Why minus? Because they're acting downward. So now my change in shear is going to be minus 20 plus a 4. It started at 4. I have a change in my shear that's minus 20 plus 4. That's a minus 16. So what you're telling me is, it ain't these guys up here. It's the last value I drew up, which is the one that goes to a negative value. Great, let's draw it in. So here, I'm going to draw in that line. There it is. So far, so good. Now you know it's a line because if it's uniform distributed, it's got to be a line for the shear, it's got to be a parabola for the bending moment. I know it goes to negative because I found the area underneath the distributed load, which happened to be minus 20. Minus 20 plus where I started, which is 4, gives me a minus 16. I know I'm going down to negative 16. Yes? Who's not with me? Now what happens? Well, I'm over here. Well, over here means I'm at By. So now I say, hey, By is 28. And I'm down at minus 16, add them. Hey, if you can add, subtract, multiply, and divide, you're good to go on this test number 3. Test number 3 is never curved. Averages between 75 and 85, easy. Lots of hundreds, lots of 90s, 95s. I will get the occasional 40 and 30. Why? Because the people that got 10 and 14 and 20 on this test will stick it out and get the 50 on the next test because they won't put in enough time to get 100. Why? Because they say, fuck it, I'm going to just take the test to see it. Right? I'm going to repeat the class anyway, so I'll just take it and look at it and try it. And if I get a good score, I get a good score. If I get a bad score, fuck it, okay. So yes, I will get those people that will generate the 40s and the 50s and the 60s. But the ones that are here to work and so forth will get the 85s and 90s and 100s. Okay? So if I add these, what do I get? A positive 12. So now I'm going to shoot up here to a positive 12. I'm not looking for scaling. That's not my goal. I don't want you to draw this 12 down here because that would be below the 4 for crying out loud. Okay? Give me a little bit of, hey, common sense and say, this is above 4 someplace. Okay? So I'm not looking for scaling, I just want to see the actual figure along with the breakpoint values. These are the breakpoint values. 4, 16, 12. And I don't want you to go, let me put the 16 over here. Let me put the 12 over here. Don't do that. Don't do that. That just becomes a bloody mess at the end. Put them at the breakpoints. Put them on the diagram like I'm doing. Now what? Well, hell, there's no load after that. What does that mean for the shear? Straight line across. So draw me a damn straight line across. Until I get to the end. What happens at the end? Well, I got a plus 12, minus 12. I go to 0. Thank you. Do I need check? Do I need ChatGPT? Do I need to beg Nora for an answer? No! None of the above. You know you fucking did it right. It went to 0. So when you leave the test, you know whether you got number 2 right or wrong. I got it right. Ding, ding, ding. Now, the only thing you need to tell me is this distance x. Why? Well, where the shear goes to 0 is a potential what? Max for my bending moment. The next diagram has a max where the shear goes to 0. means there's a large moment, which means I might have to go to the construction worker and say, hey, there's a large moment here, and its value is from the left side of the beam over, we need to brace it. You gotta tell them how far from the left side. Where do I put this brace? Well, I need to find x. Two ways to find x. The long-ass way and the short-ass way. Long-ass way first. Find the equation of that line. Yeah, remember? Y minus y0 equals m times x minus x0. What is that? Point slope form of the equation of the line. Yes? What's my m? Oh, this is a hard question. What is it? y2 minus y1, x2 minus x1. Everybody remember that one? Don't need it. You should know already without having to do any of that shit. But you can. Let's do it just for the argument's sake. M is equal to y2 minus y1 over x2 minus x1. This has coordinates here of 0, comma 4. This has coordinates of 4, comma minus 16. This says minus 16 minus 4, minus 16 minus 4 over 4 minus 0. The answer is 5. Negative. Did I really need to do that? Why not? What is dV dx equal to? Which is the slope of my shear. What's it equal to? What's it equal to? Minus W of x. Well, in this case, what's minus W of x? It's 5. This is my slope. This is my end. I didn't need to do all this bullshit. Now you can sit there and say y minus, let's take this point. 4 is equal to minus 5 times x minus 0. Y is equal to minus 5x plus 4. There's your mx plus b. So this is my shear equation. So the equation of this stupid-ass line is minus 5x plus 4. Set this equal to 0, x is equal to 4 over 5. Negative, negative, which is 0.8. That is 0.8. Yes? Who's not with me? Hey, welcome to the party. What's up? You're a little late. A little bit. A little bit. Take this number, divide by that number, and you'll get that number. That's the easy one. I don't need the equation of the line in order to find the x. Take the 4, divide by the 5, and you'll get the 0.8 every single time. 4 divided by that number will give me that. That's exactly what you're doing. Except I'm not finding the equation of that line. You with me? All right. Bending moment. It starts at 0. Why? There is no external moment out here. Right away, I see a line. A line in the shear tells me it's a parabola in the bending moment, correct? So I need the area of this triangle. That's 1/2 times 0.8 times 4. That's going to give me 1.6. So I have a parabola, and by the way, I'm going to extend this down. Because now I have a parabola that goes to 1.6, and I'm going to go from 0 to 1.6 in what fashion? The answer is a parabola. Yes, there is the other half, but I don't care about that just yet. I'm looking at just this piece right here. Yes? Everybody see what I did? Next, there is this triangle. Find its area. That's 1/2 times 4 minus 0.8 times a minus 16. That's going to give me minus 25.6. If you do the math. You with me? Who ain't with me? Now, I started at 1.6. I have an area that is minus 25.6 plus a 1.6. That's going to be a minus 24. So I know I have to continue to minus 24. But this is a line. That means it's a parabola. So I'm going to do a parabola down to negative 24. So there's the continuation of the parabola. You with me? Huh? Okay, next. I see this area. This area is base times height. Area is base 2, height is 12. This is a positive 24. Why? Because it's a positive area above the x-axis. Positive 24 and a minus 24 is
0.
0. That's pretty. I like that because I know I got to go to 0. How am I going to 0? I'm going to go via a line. Why? Because if the shear is horizontal, which it is, that's going to tell me I have a linear. So I'm going to go to 0 linearly. Bang. That's it. That is my shear diagram and my bending moment. Now, why did I do this? I did this because good old mechanics of materials, or mechanics of solids, says sigma is equal to mc over I. This m has to be the largest m that is due to the loads. Well, now I can physically see here the largest m is what? Irregardless of positive, negative, what's the largest m? What's going on here is 24. I know from the next class, VQ over IT is the shear stress. I look up here, what's the largest shear? No, it's 16. So this has to be 16 for the largest shear. That's why I'm drawing a shear bending moment diagram. I'm not doing it at a particular point because if I do it at a particular point, it might not be the largest. I can now physically see the largest by drawing the shear bending moment, and then I pluck those out and dump them into the right equation. You with? Now, I need you to tell me that x. Why? Well, because wherever the bending moment goes to 0, my rotation is a max. And where my rotation goes to 0, that's the max deflection point. Now, granted, we're not doing rotation and we're not doing deflection because we don't have that capability. Why? Because we're dealing with rigid bodies and only rigid bodies. To find a rotation and a deflection, I have to allow the beam to deform. I'm not allowing it to deform here. So we can only do 2 of the 4 diagrams. But I need you to find this x. Because trust me, you go to the next class, you're going to be drawing rotation and deflection curves. But if you don't draw a rotation and deflection curve, shame on the teacher that's teaching that class. Because they should show you this. So, how am I going to find this? Well, what created this curve? That freaking line. So I can go back, there's 2 ways I can do this. I can go back and say dm dx is equal to minus 5x plus 4. dm is equal to minus 5x plus 4 dx. Integrate this. m is equal to minus 2.5x squared plus 4x plus an integration constant, c. I'm going to move it because you can't see it. Here you go, I moved it. Yes? Now I have to evaluate that c. Well, where the hell did this curve originate at? At 0, or it originated here at 0.8 and 1.6. So at x equals 0.8, m is equal to 1.6. Plug that into there, plug that into here and here, and you'll find c. Once you find c, set it equal to 0. Oh, now I have to solve a quadratic equation. Minus 2x squared plus 4x plus whatever the value of c is. Yes? Which, probably not going to do it using factoring. You're going to do probably quadratic form. Now, there's an easier way to do this without any integration whatsoever. How many of you remember the vertex form of a parabola? I didn't think so.
Help it.
Vertex form of, I know you saw this if you had algebra. Vertex, when I write it, you go, oh yeah, I've seen it. So let me write it so you can say, yeah, I've seen it. Here you go. Vertex form of parabola. You ready? M is equal to A times x minus h quantity squared plus k. Yes, that's called the vertex form of a parabola. How many remember that now? How many saw this for the first time? Seriously? Why? A prep school should have taught you this. What prep school is that?
Really small.
How small?
Like, there was like 72 students in senior class. Like,
72 students in your class. What's the name?
Somerset Prep with locked up.
Somerset Prep.
See, it's nowhere near even in Temple. It's all the way down, like, Fort Lauderdale area.
Somerset Prep did not teach you the vertex form of the parabola.
No.
They might have, but you don't remember.
It's like a.
Oh, I'm certain.
That's sad. It's a prep school, quote unquote. H comma K, that is the coordinates of the vertex. A is the slope divided by 2. So in this problem, H comma K is really 0.8 comma 1.6. A is 5 divided by 2, which is 2.5. And it's negative, because 5 is negative. So I'm going to say M is equal to minus 2.5 times x minus 0.8 quantity squared plus 1.6. Set this equal to 0. That says x minus 0.8 quantity squared is equal to negative 1.6 divided by negative 2.5, which is a 0.64. I'm now going to take the square root of both sides. X minus 0.8 is equal to plus or minus 0.8. So I have, when I take the square root, it's either plus or minus. So therefore, x1 is 0, x2 is 1.6, which is the 0.8 plus the 0.8. If I use the negative, if I use the positive, I'm going to get 0.8, I'm sorry, the negative, I'm gonna get 0.8 plus 0.8, which is 0. And if I use the other one, it's gonna be plus 0.8. When I bring this over to the other side, plus 0.8, that's the 1.6. So you just found that this right here, it's telling you, hey, the parabola starts at 0 and it ends over here, crosses at 1.6. It crosses at 0, which is the initial, and it crosses at 1.6. That is using the vertex form of the parabola to find where it crosses. Questions, thoughts, comments, ideas, anything other than anybody? We're all good? All right.